CSC241. I'm your host, Professor McKinney. See, I'm trying to get my stream persona going, right? So I can rake in all the sweet, sweet ad revenue. Morning, Porter. All right, so let's get to it. We last time we started looking at Logisim, and in particular, we looked at what a D flip-flop is and how to therefore use it to build a single bit memory cell. And then obviously if we wanted more bits, then we would build more of these things. Okay, great. And then, align them correctly in terms of, which bit is which bit in the order of stuff. Okay, so, essentially we want to think of Logisim as allowing us to abstract upwards from, we can do stuff at the individual transistor level, but we can go, much higher than that, right? So there is the transistor here, and they, I don't want to say they work different than, so I guess none of you took 101 with me when we started doing the transistor stuff, did you? I mean, you were by virtue of TAing, but yeah, okay, anyway. So I think when I've taught 101 for a while, we talk about transistors, but we never actually built any circuits with them. So maybe a year or so ago, I said, this is silly. Let's actually build some circuits. And so I handed out buckets of parts and breadboards and said, okay, let's build an AND gate or whatever. Well, so there are lots and lots of different kinds of transistors, and the particular kind that they have modeled here in the program is the basically the way that you would build one of these on an integrated circuit, not like a single bare transistor that you'd put in a chip. Okay, and so that means that things work a little differently in terms of how you'd wire stuff up, and I'm still kind of I really need to take the electronics class that the physics department offers and, learn more of this stuff. But anyway, so you can do stuff at individual transistor level, but we'll sort of abstract one or two layers above that. And what I mean by, so here's my conception of the layers, right? You've got individual transistor level. All right. One layer above that would be doing things on gates. So AND gates, OR gates, all of that stuff. One layer above that would be aggregating a bunch of gates into things like flip-flops, registers, and so on. And then one level above that would be arranging all these different components and connecting them together to build a computer type thing. Okay, so that's sort of the hierarchy in my mind. Yeah. Okay. So we need to talk about some of the other different pieces that we've got here, right? So um, we talked about the clock, okay, and we talked about the pin and the pin and probe and the splitter. Now, some of these other things like a pole resistor, um, that we would need to talk about more if we were doing. So I haven't managed to get the GPIO stuff working. Okay, I wrote the author. He sent me back his code for doing initializing the memory mapping, and I'm worked for probably 3 hours on Sunday trying to get it to work. His code works, but it's what comes after that that I can't get to work. So, or not yet anyway. Um, so I'm going to send him my code later today and say, here's what I tried. I can't get it to work. Am I being an idiot or is there something I'm missing? I did find some bugs in his code too, by the way. So there's one of the examples where he uses X registers where you really should use W's because um, the registers on the uh, so okay, so let's back up. How do you access the the devices, the GPIO pins? Well, what you do is you access registers that control them by writing to what you think is a memory address. But it's not actually a memory address. It's mapped to the registers in the GPIO chips, right? The stuff that controls that. Okay, so the way you set these things up is to read and write memory. Well, because it's not really memory, if you try to write to 64 bytes or 64 bits, excuse me, you're trying to write to two different registers on the Broadcom chip simultaneously, and it doesn't like that, right? So you have to do it 32 bits at a time because that's the width of each one of those registers. So that tells me, of course, that the code, like, well, either they tested it but then didn't check to make sure that what was written in the book matched it, or they didn't test it. So anyway, so I'm continuing to work on that, and we'll see if we get to learn anything more about it. But right now we're kind of stuck. All right, so let's talk about the gates department. So most of these are, in fact, yeah. Is this big enough you guys can read clearly the different stuff? Okay. So most of these gates are the kinds of gates that you would have seen if we did 101, or if you had done like, you know, some digital logic or something in like robotics or something like that, right? So you got your NOT gate, AND, OR, NAND, NOR, XOR, XNOR. Okay, those are all like the usual suspects. Okay. Now, then you've got a couple other ones in here that you probably haven't seen before, even an odd parity, which we won't use, at least not for now. Okay, and then there's these things called controlled buffers and buffers. Okay, so basically a controlled buffer gives you the ability to sort of disconnect a circuit, right? So what I could do is if I have, like, let's say an input on one side and an output on the other, okay, then, and let me put an input here. Okay, so if the thing at the bottom of the buffer, the control line, is 0, then it literally disconnects the circuit, and what's on the other side is sort of floating or indeterminate. Okay, but if I make a 1 on, put a 1 down here at the bottom, then it connects it, and you get actually a 0 as the output. Okay, or a 1 at the output if I turn the thing up there high. Okay, so what you can use these controlled buffers for is, well, let's say, for example, we want to build a bank of registers, okay, which is something that you guys will build. You've got data input to the register and data output to from the register. Well, those are going to both be connected to your data bus. Well, you only want the read side or the write side to be connected to the data bus, but not both simultaneously. So you can put a buffer on either end to disconnect the side that's not actually being used from the bus, and then reconnect it when it needs to be connected, right? And that way you don't have like dueling data on the bus. Does that kind of make sense? I'll have to, yeah, we'll have to kind of see this in practice to see what I'm talking about. Okay, but it's like a little disconnect basically. Okay, so that's the buffer, and then PLA is a programmable logic array. So this would be like a oops, that's not what I wanted. You can put like, it's like a little chip that would be able to execute code based on what's input and what's output. Okay. All right. Then plexures is where I want to talk next. Okay, so we've got, let me pull up a couple of these dudes down. Okay, so we have these first two parts that are called multiplexers and demultiplexers. Okay, and they basically work, the idea is the same, it's just kind of um, which way it splits or combines. Okay, so where you would use use one of these things is, let's say, let's talk multiplexer first. Okay, so let's say that you have 4 telephones in a room, but only one telephone line to the outside world. Okay, I know this sounds kind of ridiculous. It's a contrived example. Okay, so you've got 4 telephones, and any one of the telephones, if it's picked up, can connect to the phone line and go out. Okay, but you don't want, let's say, all 4 phones to be able to get picked up and all 4 people being able to talk at the same time, because this is not actually how phone lines work, but you guys run with it. Okay, so what you could do is you could use a multiplexer. Okay, and the multiplexer, each phone would connect to one port of the multiplexer, and then the multiplexer selects which telephone is actually connected to the phone line. Okay, so you could say, all right, I want phone number 3 to be connected to the phone line. That's it. Phone numbers 0, 1, and 2, not connected. Okay, does that kind of make sense, the idea? All right, so let's configure this particular plexer for exactly that function. So in this case, I want a select bit. I would want 2 select bits, okay? And the select bits here, basically, how many, if my example, I've got 4 telephones, right? Then how many bits do I need to encode 4 options? 2 bits, right? Because there are 4 patterns for 2 bits, right? Okay, so if I had 8 telephone line or to 8 telephones, how many bits would I need? 3, because it's 2 to the third, right? Yeah, 2 to the third is how many patterns there are, and that's 8, right? Okay, so here we need 2-bit input, okay, and let me connect these things here. So let's say, let me put this guy here, and then you notice how in orange it says incompatible widths? That is sort of an error checking thing, and it tells you, oh, okay, you're trying to connect a 2-bit thing to a 1-bit thing. You can't do that, right? So that's kind of nice. All right, so the selector line is down at the bottom, and then you see each of those 4 little blue dots up at the on the left-hand side of the multiplexer. Yes, those are the telephones that get plugged into it. And then the single line that's on the right would be the telephone line that goes out to the outside world. Okay. So if I, for example, let me just use some lights, a light here. Okay. And then let me use some input pins. Well, when you want to be able to connect multiple things to a single data line, okay, so for example, well, um, yeah, so, okay, so right now, if the select bits are 0, 0, then the top input is the one that's connected. And if I change the other bits, nothing happens. If I change this, then it's selecting the first line or second or third, depending on which select bits I put, okay? All right, so this would be useful anytime you want to have, well, like let's take, for example, an ALU, okay, where you have, so an ALU, right, arithmetic logic unit, where you could do addition, you could do, say, subtraction, you could do logical anding bitwise, logical ORing bitwise, right? There's lots of different operations. Well, the output of each of those would get connected to a multiplexer. And then the multiplexer would output to the data bus. And you'd say, okay, which operation did I actually want here? Right? Was it this one, or and so on? Okay, does that kind of make sense? So maybe another example of this would be um, the well, okay. Uh, let's hang on. Let's go to the other thing, and then I think you guys will see the utility of this. So a demultiplexer works basically the same way, but instead of going from a bunch of things to a single thing, it goes from a single thing to a bunch of things. Okay, so it's like the reverse of a multiplexer. Okay, now where would you use that kind of thing in a computer? Well, let's say that you had a printer and a scanner and a external hard drive and a modem. I'm making up stuff here, right? You could use a demultiplexer to decide which of those peripherals was connected. Yeah? No? Does that kind of make sense? Right. But it's the same idea as a multiplexer. It's just going the opposite direction. Okay. Um, okay. So same idea. You have selection bits, however many there are, and if you've got n selection bits, then how many connection points do you have? 2 to the n, right? So if you want 16 connection points, you need 4 select bits, okay, because there are 2 to the 4th different patterns for 4 bits. Okay, then a specialized version of the demultiplexer is called a decoder, okay? And a decoder is basically just like a demultiplexer, except it has an extra input, which is to enable or disable it. Okay, so it's kind of got like a built-in buffer. Okay, now it's called a decoder for a good reason. Okay, so let's think about, and I know it's been a while, but let's think about the Brookshire architecture. Okay, how many different opcodes were there? There were 12 that got used, but theoretically there could have been 16. Okay, it's just that 4 of them were unused in the original specification. Okay, so where we would use a decoder would be part of, or could use a decoder, okay, would be to have 4 select bits, okay, and then in hex, or like in the Brookshire architecture, what was the opcode? The opcode was a 4-bit segment that told you which operation you were doing. Hmm? Yeah, is the first 4 bits of the instruction. Okay, well, those 4 bits become your select bits. Okay, and then you connect this to a decoder, and it activates exactly one of the 16 lines here, the one corresponding to whichever instruction you have. So what you would do is you would say, okay, what happens in the situation where the opcode is number 1? Well, I would connect the control lines to make whatever that does happen to the uh, pin number 1 here. Okay, and then opcode 2 is different. That one would go there, and so on. Okay, so I could use this then to control like which thing happens or which circuit I'm powering on. Yeah, Evan. No. Okay, good point. So notice the one difference. Well, there's two differences between the decoder and the demultiplexer, right? A demultiplexer doesn't have an input. There's not a blue dot here, right? So demultiplexer connects one wire to two to the n wires and selects which one actually gets connected. Okay, a decoder just says, okay, which of these however many lines am I going to turn on? But I'm not passing input to it. Okay, I'm just saying which one do I want to turn on? Uh-huh. That'd be the opcode, right? So the opcode would get connected here, okay, to the select bits, and that would select. So like, let me just connect something to it. All right, so I need a 4-bit input because in Brookshire, the opcodes were 4 bits. Oops, I'm sorry, connected it to the wrong spot. It was this one that I wanted. That one's the enable. Okay, so let me have a single bit there for the enable. Okay, and then let me just, for sake of demonstration, put a light here and a second light there. And I'm going to connect that one to number 1 and this one to number 2. And then I'm going to change the color so that we can tell the difference between them. Okay, so if I make opcode 1 was, in Brookshire, was to load a register with the contents of a memory address, okay, and 2 was to do a specific bit pattern, okay, so to load an immediate. Okay, so if I make my opcode 1, okay, so 0001, then nothing happens, okay? Why? I haven't enabled the circuit, okay? So I need to enable the decoder by setting this other bit to a 1, okay? And now the decoder says, okay, 0001, I'm going to decode that and power up the output number 1 out of my 16 ones, 0 through 15, right? Okay, now what about if I change the opcode bits down at the bottom to a 2? Okay, then it connects the second dude and powers it on. Okay, and then I could do the same for the rest of them, right? Same idea, just a lot more stuff to wire up.
You program the decoder to say, okay, I want to do something for memory cell to register, so I program.
Far, that's like 3 levels up from where we are. Okay, like, but that's what, exactly. That's where we're working towards. Okay, so the decoder doesn't program anything, right? The decoder just says, okay, which of these 16 lines am I going to turn on based on the bits down at in my selection thing? That's it. Okay, so if I had something that, like, let's say in the Brookshire, where with Brookshire, what do I need to do, right? For opcode 1, I need to do the following sequence of things. Take the memory address, go out to memory, enable read on memory, enable the address to be whatever was in the opcode, get the data from memory, put it into a register, and write it to the appropriate register, right? So that's a sequence of events, right? Well, how do I know to start that sequence of events if one of these output wires is on? Okay, that sort of activates it. That's how we would use it to activate. Okay, does that make sense? Okay, now you can do a bit fancier version of this, which is called a decoder ROM. Okay, so you can have a ROM chip here. So, for example, okay, if I had 4 address bits, then that allows me to address 16 different things, right? Well, what I could do is I could say, all right, let's say that if I have opcode 1, I need to do these 12 things. Well, I could kind of condense a bunch of stuff into the decoder ROM, okay? But let's forget about that for the moment um, and stick a bit more low level with the decoder, okay? Okay, so then there's also this thing called a bit selector, which is um, you can kind of get this with the splitter, right? If you want. But like, let's say I need to know bit number 7 of a byte or something. You know, I want to strip out and know a particular bit. Then I could use this thing. Okay. Um, and let's look at the different options for it, right? So I have data bits and output bits. So I could, for example, right, select 4 bits out of 8. Now, in general, I think I like to use splitters for this because what you can do is, let me go to the wiring tab, let me go to splitter. Okay, so for Brookshire, let's say, for Brookshire, right, an instruction is how many bits? A full instruction. The opcode is 4 bits, but a full instruction would be how many? Keep going. 16. Okay, right, because it took 4 hexadecimal characters. Okay, so the first 4 correspond to the opcode, and then so what I can do here is I could say, all right, let me take a 16-bit splitter, and the first 4 0 through 3 bits, or actually those would be the last 4, right, because of the Indianness problem. All right, so 12 through 15 would be the last 4 bits, or first 4 bits, bleh, because of the order. Sorry, this really is annoying, isn't it? Okay, but I could split it out in groups of 4 bits. Okay, and I could say I want these 4 bits to go here, and those 4 bits to go there, or whatever. Right? Is that okay? Okay. So, so I've